We begin this lecture by the step response of a first order circuit. First of all, we have to be precise about what we mean by step response. So therefore we have to define what this is, and step response in general is applicable not only to first order circuits but general nth order systems. Okay, and what it means is the following. Step response is the zero state response, okay, for a unit step excitation. So the step response of a circuit is its zero state response remember that by definition, in zero state response, we set all the initial conditions to zero. All the capacitor voltages are set to zero, and all the initial inductor currents, initial inductor currents are set to zero. To a unit step excitation. Okay. So it means, therefore, in other words, the following. We set initial conditions to zero. Okay. Note that this definition is applicable to the general case, therefore, for an nth order circuit. So by setting initial conditions to zero, once again, it means you set all the initial capacitor voltages to zero. So the capacitors are initially chargeless, and you set all the initial inductor currents to zero. So the inductors are initially fluxless. Okay. Then we apply from the input. And by input we mean the voltage provided by some independent voltage source, or the current provided by some independent current source. The waveform u of t. Okay. Now by input we mean the current from independent current source or voltage from independent voltage source. That's part of the circuit. And remember what unit step was. Unit step is a function that's zero for all negative times and 1 for all positive times. Okay, so it's clear why we call it step, and it's clear why we call it unit step, because it jumps to unity 1. Okay, now this is the definition of a step response. Now we're going to take this definition and apply it to a first order circuit. Okay. Example. Find the step response for the following circuit. This is the input. You can have input. Now, L, R, and this is the resistor voltage. Okay, now it's clear that because we have a single input, it's clear that from where we're going to set, we're going to apply this waveform. Okay, so IST will be this waveform. Okay, to figure out the step response. Then all the dynamic components must have zero initial conditions. Therefore, we have a single dynamic component in this LTI inductor. So initially, by definition, its initial current is set to zero. Okay, there is one thing that's ambiguous at this stage, okay, or it's not given. It's the step response for what? So we also need an output. Okay, so an output could be any one of the branch currents or voltages. Okay, so what we're asked for is step response for the resistor voltage. Okay, so what we're going to find now is we're going to set the initial inductor current to 0. From IST, we will apply this function, U of t, and we're going to figure out what happens at the resistor voltage, okay, VR. So, to do that, let's obtain the differential equation. Okay, so we will have the differential equation, we have the initial condition constraint, which by definition, the initial condition is 0, and then initial condition of inductor current is 0, and then we're going to figure out the answer. So what's the differential equation? DIL equals 1 over L VL. Okay, now let's work with IL. So as if we asked for the step response for inductor current, but once we have the inductor current, we can clearly figure out every other variable. Okay, so let's deal with the inductor current. So that's where we start from, the thermal equation for the inductor current. DIL equals 1 over L times the voltage VL, and clearly this voltage is VR. Everything is parallel in the circuit. And that's 1 over L R times IR, excuse me. Okay. VL is VR and VR is RIR. Thermal equation of the resistor. And finally, 1 over L, because we want in our equation only the formulation variable, which is in this case inductor current and the terms coming from the input. So we want only IL and IS. Hence, we have to re-express this current IR according to that purpose, and we can easily do that using KCL. Okay, so IR is IS minus IL. Minus IL. Okay. So reorganizing the terms gives us what we want. DIL plus R over LIL equals the right hand side, which is non-zero because we have some non-zero input. IS. Okay. And now we will try to figure out what happens if IST is set to unit step U of t and IL 0, initial inductor current is 0. Okay. So for positive times, first of all, for negative time, nothing happens, okay? So initial condition 0, this is 0 because U of t is 0 for t negative, and then everything is 0. So things begin to change for positive times, and that's what we try to figure out. For t positive, we can write DIL plus R over LIL equals R over L. IS is U of t, and U of t for t positive is constant 1. So therefore we have the following equation, R over L. And the initial condition, by definition, is 0. Okay. Initial inductor current is 0 because we are trying to figure out the step response, and by definition, all the initial conditions are 0 for the step response. So, we know how to deal with this case. We have the differential equation, we have the initial condition. The differential equation is non-homogeneous, therefore we will have homogeneous part and particle part. We're going to figure those out, put them together, and finally apply the initial condition constraint to find the unknown that appears in the homogeneous solution. Okay. So, homogeneous solution IHT equals some constant K e to the natural frequency times T, and natural frequency in this case is R over L. So that's homogeneous solution, and this for all k solves the homogeneous version of the differential equation. That you set the right hand side to 0, and you have DIL plus R over LIL equals 0, and that equation is satisfied by this class of this family of solutions, okay, for all k. And then particular solution. Okay, to determine first the form of the particular solution, we look at the right hand side. Right hand side is constant, therefore the particular solution will be constant. And to figure out what that constant should be, what we do is we take our particular solution candidate and plug it into the differential equation, and it immediately gives us what the particular solution should be. Note that the particular solution is independent of what the initial conditions might be. Okay. So particular solution IPT equals right hand side is 0, so the particular solution will be this form A. And then what you do to find particular solution is you put this candidate into the differential equation. A is constant, therefore derivative of that constant is 0. So what we have is R over L times A equals R over L. Clearly A must be 1. Okay, R over L, A equals R over L, hence A equals 1. So the particular solution is determined. So we have IL of t equals IHT plus IPT. That's 1 plus K e to d natural frequency times t. Okay. Now K is still unknown, and for that we will use something that we haven't used so far. We can evaluate this expression at t equals 0. Plugging t equals 0, this becomes 1. So we have k plus 1 is IL 0, and that must be 0. Hence, k is minus 1. Okay, initial condition constraint 1 plus k e to d minus R over L t evaluated at t equals 0 must be 0. That means k has to be minus 1. So we figured out ILT, and that would be the step response for the inductor current. But we're not asked for the step response for the inductor current, we're asked for the step response for VRT. And for that, we have to, starting from the inductor current, we have to figure out VRT. So we have IL t equals 1 minus e to the minus R over L t. Okay, for t greater than 0. How about for t negative? Like for t negative, everything is 0, so we don't have to. There's nothing interesting going on for the negative times. So this looks like the following. 0, t, and this is R, IL, t. Initially at t equals 0, it's at 0. Okay, as t, because 1 minus 1, it's 0. As t goes forward, as t becomes larger and larger, this thing here becomes smaller and smaller. It approaches 0. Okay, so the overall term, therefore, in the limit approaches 1. So what we have is, therefore, this is 1, something like this. Okay. That's ILT. Now, next question is, which was what we were asked in the first place, is the voltage of the resistor, the RT. Okay, so let's figure out the RT. The RT is R IRT, and I KCL is IST minus ILT times R. That equals R times this is 1 for t positive minus ILT. 1 minus e to d minus r over L t. Okay. So that's r e to d minus r over L t for t positive. So that's r. So this is the step response, okay, for the resistor voltage. And it looks like for T0 ER T. At T equals 0, it's at R. And as time goes on, it becomes smaller and smaller because that exponential term is decaying towards 0. Okay, so that's VRT. Instantly, we could have figured out VRT using the Fermi equation of the inductor, because VRT is VLT and VLT is L VILT. Okay, so that's another way to reach the same conclusion. Okay, now let's consider a different input. We have the constant input. We have so far considered only constant input. Now we're going to figure out what happens in different situations. Here's our next example, where the input is quite more interesting than a constant input. Okay, let's deal with sinusoidal input. So this is the circuit. That we will study. This is the input of the circuit, okay, independent voltage source. We have a switch here that closes at t equals 0, and when the switch closes, all these three components become series in a loop. R, L, and this is IL. So VST is of the form V0 cosine omega t plus phi. So this is the magnitude of the oscillations. This is frequency of oscillations, omega, radians per second, and this is the phase, okay, of the sinusoidal function. Now for this input, we're asked to find ILT for future times for t positive. Note that the only reason for the switch here is to tell us indirectly that the initial inductor current is 0, because initially this is open. Open means there's no circuit, excuse me, there's no current flowing over the components. Therefore, IL initial, IL0 is 0. Okay, and then once this switch is closed by KVL, the voltage of this guy and that guy must equal VST, and that constraint, that forcing term will generate some current over ILT, and we're going to figure out what that current is now. Okay, so the solution is, or the solution approach is the same. We obtain the differential equation first, okay, and by looking at the differential equation, we determine the homogeneous solution and particular solution. Once we have homogeneous solution and particular solution, we put them together, obtain the overall solution, and finally to that overall solution we apply initial condition constraint. In this case, initial condition for our formulation variable is 0, and after that everything will have been complete. Okay, so let's obtain the differential equation. Therefore, solution L DIL equals VL. Okay, so we start from the terminal equation for the inductor. IL is our formulation variable. Therefore, we want to express everything in terms of the formulation variable and the non-zero input Vs. So let's do that. VL is Vs minus this voltage is plus minus, this voltage is R times IR, IR is IL, therefore this is R times IR. Okay. From which immediately follows DIL plus R over L IL equals 1 over L times the input Vs. Okay. Therefore, DIL plus R over L IL equals V0 over L cosine omega t plus phi, because Vs is given to be this sinusoidal function. This is the differential equation to be satisfied by our inductive current. And what's more, we have IL0 equals 0, which we gather from this switch. Switch open means that initially no current can be flowing over the inductor. Okay? And the solution that we would have found should satisfy both of these constraints. Okay, so this is the differential equation constraint, and this is the initial condition constraint. Okay. So we have the following, this differential equation with a non-zero right-hand side, therefore it's not homogeneous. That means the overall solution will have two pieces, the homogeneous part and the particle part. Homogeneous part is easy to figure out because all you have to do is just ignore the right-hand side, ignore the input. So what you have is the IL plus R over L IL equals 0. So that's the first order homogeneous LTI differential equation, and we know the structure of the solution for it. Okay, it's some constant k times e to the natural frequency of the circuit times t, and natural frequency of the circuit is minus R over L. Let's write that down. Okay, homogeneous solution will have the following from I h t equals some constant k, then e to the times R over L times t. Now, this is new. Okay. What should the particle solution be for this type of input? Okay. When we have considered only constant inputs so far, and when the right-hand side is constant, the particle solution has the same form as that constant input, that is, it also is constant. Okay. Now, when we have this sinusoidal right-hand side, again, the general idea remains the same. The particle solution must have the same form as the input, as the right-hand side. And what the same form means in this case is the particle solution must also be a sinusoidal function with the same frequency, omega. Okay? Therefore, the particle solution must be, okay, some magnitude cosine omega t plus some phase. Okay? A cosine of phase can be written as the sum of a phaseless cosine and a phaseless sine. So let's do that. IPT, particle solution, must have the following structure: A cosine omega t plus B sine omega t. Okay? Once again, this particle solution has the same form as the input, by which we mean that it's also a sinusoidal function with the same frequency. Okay, so this frequency is not arbitrary, but it's determined by the frequency of the input. So we have to determine, so the sum of these two terms, IHT and IPT, will give us ILT. Therefore, the question at this point is, how should we figure out the three unknowns, A, B, and K? Okay. So let's figure out A and B first, because we have to do that first. And to figure out the unknowns regarding particle solution, we require only the differential equation. We don't care about what the initial conditions might be. Okay, so this is our particle solution candidate. We take this, put it into the differential equation, and we will have enough many equations to determine our two unknowns A and B. So let's do that and see. So to be determined at this point are A, B, and K, three unknowns. Use the differential equation to find the particle solutions unknowns A and B, and then use the initial condition constraint, okay, which is to be applied to ILT, not IHT. And ILT is IHT plus IPT, okay, to find K. Okay, so let's move on. dIP plus R over L IP, and IP is our particle solution, equals E0 over L cosine omega t plus phi. Okay. And it's useful to employ the following trigonometric identity. Cosine of sum of two terms equals cosine alpha cosine beta minus sine alpha sine beta. Okay, so let's also use that trigonometric identity to write this cosine with phase as sum of cosine and sine both without phase. Okay, d over dt, A cosine omega t plus B sine omega t. This is our particle solution candidate. Plus R over L, A cosine omega t plus B sine omega t equals V0 over L. And then we write that cosine as a phaseless cosine and a phaseless sine using the trigonometric identity here. Okay, times cosine phi cosine omega t minus sine phi sine omega t. Note that cosine omega t is time varying thing, is a function, whereas cosine phi is fixed because phi is fixed. Likewise, sine omega t is oscillating, whereas sine phi is fixed. Okay. So let's proceed by performing the differentiation here. What we have is minus A omega sine omega t is the derivative of this term, plus B omega cosine omega t, derivative of this term, plus A R over L cosine omega t plus B R over L sine omega t. Okay. And that equals omega 0 cosine phi over L cosine omega t minus omega 0 sine phi over L times sine omega t. Okay. Now this, okay, our particular solution satisfying this differential equation means that this equality holds for all times. Okay. And what that means is the following. So what we're going to do is we're going to collect the cosine terms and we're going to collect the sine terms. So if you collect the cosine terms, okay, we have here 1 b omega, we have another one plus AR over L, and finally we have omega 0 cosine phi over L. Let's carry it to the other side, minus omega 0 cosine phi over L. Okay, so those are the old cosine terms. Plus, let's collect the sine terms. We have here minus A omega. We have here plus BR over L sine omega t. And here we have this guy carried to the other side plus omega 0 sine phi over L sine omega t. And that must equal 0 at all times. Okay. Now, because cosine and sine, they are linearly independent functions, this equality holding at all times means that this must be 0, this coefficient of cosine and this coefficient of sine must also be 0. Okay? Well, to see that, plug in t equals 0 and sine disappears and this becomes 1. So what we have is this thing equals 0. And then plug in t, that is pi over 2 omega. In this case, cosine becomes 0, sine becomes 1, and then this coefficient of sine must be 0. Therefore, this equals 0, and this equals 0. We have two equations, which is good because we have two unknowns, A and B. So let's write down those equations in a nice form. Equals that. Okay. Now this is the vector of our unknowns, A and B. Okay. For the first row, let's get the first equation, which is here. We have R over L for A. For B, we have omega, okay, and the right hand side equals omega 0 over L cosine phi. Omega 0 over L cosine phi. For the second row, let's look at the second equation. For A, we have minus omega. For B, we have R over L. And the right hand side is minus that guy. So we can figure out A and B by simply multiplying both sides with the inverse of this matrix. If you do that, this is what you have. A, B equals omega 0 over L. Okay, we take this guy outside, divided by, okay, times the determinant of inverse of this matrix, times the vector cosine phi minus sine phi. The inverse of that matrix is 1 over determinant times adjoint. Okay, the determinant is R over L squared plus omega squared. Okay, and then adjoint is you slap the diagonal terms and you negate the anti-diagonal terms, and that multiplies this guy, cosine phi minus sine phi. Note that this omega 0 over L terms we collect in the numerator. Okay. So, from this point on, we can assume that we know A and B because we obtained an expression for them. What remains at this point is the determination of K, the coefficient that sits on the homogeneous solution. ILT therefore equals I homogeneous plus I particular. and that is k e to the minus r over L t, homogeneous part, plus a cosine omega t plus b sine omega t, and this is the particular solution. And at this point, a and b are no longer unknowns because we just computed them. To determine k, we use initial condition constraint, and due to the fact that the switch was open, tells us that IL0 equals 0. So initial inductor current is 0. So that constraint has to be applied to the overall solution ILT. Plugging t equals 0 here, sine goes away and cosine is 1. So what we, and this guy also is 1. So what we have is k plus a equals 0, which gives us k to b minus a. K equals minus a. So the solution now is complete. ILT therefore equals minus a e to the minus r over LT plus a cosine omega t plus b sine omega t. Okay. After the switch is closed for t greater than 0. Now what happens to this solution as time goes on is, note that here we have a cosine omega t plus b sine omega t that can be represented by a single sinusoidal function. That's a magnetic phase, and the frequency will be omega. Therefore we have a sinusoidal term plus this exponential term. This exponential term, or the effect of that exponential term, can be observed, okay, in a significant way only in the beginning of time, okay, as time goes on, because this exponential term is decaying. The effect of this guy, or the contribution of this guy, will become smaller and smaller. Okay, and in the limit, that is for t quite large, we can just ignore this part, and what remains is only the sustaining oscillation sinusoidal part. Okay, therefore, for that purpose, for that reason, this part, sometimes called the transient part, because it has some contribution only in the beginning, okay, and the remaining part is called the steady state part. Okay, of course, this is a different steady state than the steady state we have seen, which was DC steady state. This type of steady state is called the AC steady state or sinusoidal steady state, which we will study in detail in 202, okay, next semester. Okay, before we end this lecture, let me quickly tell you something about the superposition for dynamic circuits, in which we're going to extend the superposition principle, which we talked about for LTI resistive circuits, to dynamic circuits. Superposition in linear dynamic circuits. Okay. Now, what we'll be talking about now is not just peculiar to first order circuits. It's true for the general case and for the circuits. Okay. So let's therefore talk about that. Suppose that this box represents our linear circuit, okay, which is driven by some input. Let's call it W of t. And by input we mean the general case where we are allowed to have a number of independent voltage sources and a number of independent current sources. So all those voltages and currents together make the input vector of this circuit. Okay, so this is the input. Also, well, the output or the response does not only depend on the input, clearly, because for dynamic circuits, initial conditions are also important. Okay. So we also have to consider them in our analysis. Okay. And then, together with the input and initial condition, the circuit is run and we obtain some output. And by output, we mean some voltage or current over some branch. Okay, that is of interest to us. So the output. Okay. So initial conditions. Let's collect them in a vector. We call it the initial condition vector. And by initial conditions, we mean all the initial capacitor voltages and all the initial inductor currents. So VC1, 0 minus, VC n, 0 minus. Suppose that we have n capacitors, so that makes n initial capacitor voltages. And IL1, 0 minus, IL n, 0 minus. And suppose that we have n initial inductor currents, so that makes n initial inductor currents. Okay, so n plus n, that makes an initial condition vector of size n plus n. Okay, so this is an n plus n order circuit. Okay, well, we usually work with column vectors, therefore let's transpose that. And as for input, it also is a vector, but its entries are functions of time. W of t equals Vs1 t Vsp t. Suppose that we have p independent voltage sources and q independent current sources, Is1 t Isq t transpose. Okay, and this vector of size p plus q with time varying entries is what we call the input vector. Okay, so in general, this signal, some voltage somewhere in the circuit or some current somewhere in the circuit, is a function of this input, okay, input vector, and this initial condition vector. So note that. Y of t are output, and we now consider a scalar output, but you can also generalize that to a vector. But for simplicity, let's take the output to be scalar. Y of t equals y t. It depends, it's a function of x, okay, the initial condition vector, and a function of the input. Okay. This is initial condition, which is a vector in general, and this is the input signal. Also in general a vector. Okay, now how about superposition? Now we're going to see how the output depends linearly to the initial condition and also to the input. And that piece of information could be useful in circuit analysis for dynamic circuits. Now we can write the following. Okay. Three different aspects of superposition which can be written down compactly in just one single property, but let's write them separately so that we can see certain things in a clearer light. Okay. First type of superposition is Yt. Alpha 1 x1 plus alpha 2 x2 0 equals alpha 1 y. T x1 0 plus alpha 2 y. T x2 0. Okay, this is called superposition with respect to initial conditions. interpret what that equation means soon. Then you can write yt0 beta 1 w1 plus beta 2 w2 equals beta 1 yt0 w1 plus beta 2 yt0 w2. Okay, and that's superposition with respect to input. Okay, and finally, the third one, yt alpha x beta w can be written as alpha yt x0 plus beta yt0 w. Okay, this is superposition with respect to both input. Okay, now let's try to put these equations in words. Suppose that you perform 2 experiments where you deal with zero input response. Okay, so you have a circuit, an arbitrary order, and you're considering zero input response. Therefore, inputs is zero. You set the initial conditions to certain values, certain capacity voltage and certain inductor currents, and you run your circuit and you obtain the response. Okay, you obtain the output, and this is the output in that case, and you record it somewhere. And then you go back to your setup and perform a new experiment. Again, it's zero input response. This time you set two initial conditions to some arbitrary different values, okay? Different set of capacitors and different set of initial inductor currents. Okay, and you obtain the response and you record it somewhere. Now, if your circuit is linear, if you, in the third experiment, suppose that you perform again a zero input response experiment, where you set the initial conditions to a linear combination of the initial condition from the first experiment and the initial condition from the second experiment. Okay? And the response in that case can be written as the linear combination of the previous responses, where the coefficients in linear combination, alphas, are the same as the alphas that you use to generate the third experiment's initial condition. Okay, so that's proposition with respect to initial condition. That concerns the zero input response. Now let's move on to zero state response. In the second scenario, we're considering the circuit where all the initial conditions are set to zero. We have only inputs, okay, or external inputs. You perform your first experiment with some input, W1. You perform your second experiment with another input, W2, and you collect your measurement. Okay, this is measurement from the first experiment, and this is measurement from the second experiment. And then you go and perform a third experiment where the input that you apply is a linear combination of the previous two inputs that you used in your first two experiments, and the response of the third experiment can be written as linear combination as such. Okay, and that's called superposition with respect to input, where we're dealing with the zero state response. And then this is a general case, in a sense, where both the initial conditions and the input are allowed to be non-zero. You perform, okay, and then you perform an experiment by setting the initial conditions to zero, by killing all the sources and only letting, setting the inputs to zero and letting only the initial conditions drive the circuit. And in the second case, you perform the zero state response, where you set the initial conditions to zero and you let your sources be active only. Then, in this third experiment, if you use a scaled version of the initial conditions that you use in the first experiment and a scaled version of the inputs that you use in the second experiment, then the overall response can be written as a linear combination of the first two responses. Okay. So therefore, superposition is extended for dynamic circuits in the following way. And the extension is due to the fact that the output, unlike resistive circuits, not only depend on the input, but also depend on the initial conditions.